Okay. So again, we're looking to factor. I'm just going to identify the terms here. I have 3 terms. I still want to look for a greatest common factor. I don't want to lose this. This is important. Okay. Now, there is just 1x squared here, if we want to consider that there's just 1x squared here. So since we have constants and variables, we can go down the list of multiples and see what we can pull out of each of them. Since this is only a 1, though, even though there's multiples of 4, like 2, and multiples of 3, like 3 and 1, I can't actually factor a common factor as a constant out of all 3 of them. Remember, if we're looking for a greatest common factor, we want to pull it out of all 3 of them. And we can't do that. And even though these two have x, this one does not have x. So, again, we can't pull any variables out. We can't pull any constants out. So step 1 in our priority list is done. Now we're looking to go to the step 2 and say, well, can we factor anything further? Well, since we have 3 terms, there are methods for factoring 3-termed expressions. Now, I did write the AC method, which is a little bit more overarching idea, but I'm going to do what's kind of called like a guess check kind of method, just to kind of make sure as we're working this out that we can check to make sure all the terms are going to go. Now, in general, 3-termed expressions have the ability to factor into 2 binomials. Okay? And what we can consider is that the first 2 terms in these binomials should multiply to equal this first term. And the second 2 terms in these binomials should multiply to equal this last term. So this will get us all the values that are required or possibly required to make this happen, but we still need to make this middle term, and the middle term is going to be based off of the idea of distributing 2 binomials against one another in multiplication, and the outer 2 and the inner 2, depending on what their signs are, we're either going to add them or subtract them based on the signs to get back to this middle term. So we're doing like a guess check type of method because we know what's supposed to happen. Now, what we did here is just redistributing what 2 binomials would be distributed back out if we're doing multiplication on 2 binomial polynomials, and it should result in a trinomial. Okay, so it doesn't matter that this is a quadratic, like a 2-degree, a 2nd-degree polynomial. But 3 terms in general can factor it to this setup. Possibly, we would just have to check it. And that's what we're going to do. Okay. All right, so since I kind of wrote all this down, I'm just going to write another set of parentheses right underneath it. Kind of go through this. So we know that the first 2, again, should multiply to equal this first term. Now, 1 and 1 multiply to 1, so I'm not really concerned about the 1 here. I'll just put a couple 1s here. The only way we're going to get 2 expressions to multiply to equal x squared would be x and x, because x times x is x squared. And there are no other options. So since there's no other options here, I'm just going to write them down. Now we're looking here. These 2 need to multiply to equal this last term, so we're going to consider the multiples of 3. Now, 3 only has one group of multiples, 1 and 3. And the way we're going to do this here is that since this original term, what we would call a leading coefficient, because it's on the largest degree term, is just a 1, this process is very simple in compared to what it could be if there was another coefficient here besides 1. So since these 2 end up being just 1, we're going to kind of condense the method here, and we're going to say that we're really just looking for a group of the multiples here that can add or subtract to this middle term here. All right, we can kind of ignore the 1s, and we'll talk about factoring trinomials where it's not just a 1 here later on. Okay. Now what we can consider is that now that we know what the multiples are, we need them to either add or subtract to this middle term. So let's kind of consider what I mean by that. So if I were just to add these two terms together, 1 and 3 would be 4, right? Or if I were to subtract the terms together, I'll just put the larger term first. 3 minus 1 would be 2. Now, this could be a positive 3 or a negative 3, a positive 1 or a negative 1. But the difference between these two is 2. And the sum of these two, if we were to add them together, is 4. So as long as one of these options is what we're looking for, then we're good, right? I mean, this isn't going to help us. We want to add or subtract to be 4, so we can make this happen here. So when we come back to our multiples, we want to consider what kind of 4 we're looking for. We're looking for a positive 4. So if this term, this middle term, is a positive value, whatever this sign is, if this is a positive sign, the larger of the two must be the same as that side. So we know that this has to be a positive 3. Then we can consider, well, what does the sign on the 1 have to be? Well, would we add 1 to 3 to make 4? Or would we subtract 1 from 3 to make 4? And we know that if we add 1 and positive 3 together, we'll get a positive 4. So we know that this is going to work out. Now we want to make sure that this guy works because they're supposed to multiply not only to be 3, but now that we've added signs, we need to make it a positive 3. Now we know a positive number times a positive number is going to equal a positive number, so that works out. And we chose from multiples of 3, so 1 times 3 we know is supposed to be 3. So before we plug them all in, we're checking to make sure that this distribution works itself out. Now, since these are both 1s, it doesn't matter where we put these two. So for now, the process is pretty simple. Whichever order you put them in, we're just going to put these guys in here. But again, if we redistribute to make sure, if we're not sure that we factored it correctly, we know that this first term is going to be distributed to each term here. So we know that x times x is going to be x squared, and x times 3 is 3x. And then we want to distribute this second guy as well. So 1 times x is x, and 1 times 3 is 3. And if we can combine like terms, I only have one x squared term, so here he is. And then I have 2x terms, so 4 and 1 altogether makes 4 of them. I'm sorry, 3 and 1 makes 4 of them. And then we have this leftover 3 here. And is it exactly what we started with? Yes. So we know that this trinomial will factor into x plus 1 and x plus 3. So the way all these get put together is just thinking about the distribution. We know that the first two, x times x, kind of like we said, have to equal this one. We know that the last two, 1 times 3, have to multiply to equal this one. And then since these two essentially get added together, we want to make that middle term. Okay? So just because we have a trinomial doesn't mean it's going to factor out. That's why we're checking to make sure that all the pieces work. But if it does, then we're good. All right, let's try another one. Okay. So since we went through the process here, this should go a little faster, right? Still going to consider how many terms I have. I have 3, and I'm going to look for a common factor from all of them. This one doesn't have any coefficients, so I definitely can't pull any constants out. And this one doesn't have any x's, so I know I can't pull any x's out. That's okay, though. At least we tried. So now we're going to go with how many terms. This is a 3-term expression. So we're going to use this trinomial factorization that we worked out here. Right? The AC method is a variation of what we did, but we'll talk about that later. So we know that 3-term expressions have the ability to factor into 2 binomials. So I just want to make sure that all the pieces work out. I know these first two are supposed to multiply to equal this first term. And again, since it's just a 1x squared, the only multiples of 1 are 1 and 1. And the only way we're going to get 2 things to multiply to x squared is if it's x and x, right? So it's my only option, so I'm going to go ahead and write it in. Now these two have to multiply to equal 10, right? So we want to consider what values multiply to equal 10. Well, of course we know 1 times 10 multiply to 10, but 10 can also be made from 2 times 5. So these are all of the sets of numbers that can multiply to equal this guy. Since these are both 1s, I don't have to really worry too much about them. So we're only going to look at, since these are 1s, which pair has the ability to add or subtract to make this middle term, which is 3. So again, I'm going to consider what we would add or subtract these two, just to kind of get a sense of what I'm trying to explain here. So we can say that if we were adding these two together, that would make 11, and if we were subtracting to find the difference between them, that would be 9. Now we're looking for them to either add or subtract to 3. So neither of these are going to work. So since there's no way that these two multiples can add or subtract to 3, it can't be that set. But let's consider 5 and 2. We can say that 5 plus 2 is 7, and the difference between 5 and 2 is 3, and we're looking for 3. So here's what we're going to try to do. We're going to try to make our 3 here. So 5 and 2 have the ability to make 3, so now we just need to consider if they're positive or negative values. So we know, based on what I was saying, that if this guy is positive, then the larger of the two must be positive. So since 5 is larger, this one's going to be the positive guy. Now, this is either a positive or a negative as well, so we just have to consider, well, if we add a positive 5, would we add 2 or subtract 2 to make 3? Well, if we added it, it would be 7, and that's not what we wanted. So if we subtract it, 5 minus 2 is positive 3, so we can see that that's going to work. Let's make sure we got this guy, though. 5 times 2 is 10, but we also want to make sure we have the sign, because we just put in the signs at the last part. So a negative number times a positive number is a negative number, so this is going to work out. So again, since these two are just 1s, this simplifies the process a lot. I'm just going to put the negative 2 in the first spot, positive 5 in the second spot. Again, I'm going to redistribute just to make sure. That's the great thing about factoring, right? So I'm going to distribute the x. So x times x is x squared. X times positive x is positive 5, right? Then I'm going to distribute this second term. Negative 2 times x is negative 2x. Negative 2 times 5 is negative 10, right? And then I'm going to combine like terms. I have only a single x squared term. I have two x terms, so I can put them together. How many x's do I have altogether? Well, 5 of them minus 2 of them is positive 3 of them. And then I have only one constant left over. And we can see that it factored out when we distributed back out to what we started with. So we know we did a good job. So this thing, I'll just come down here since I wrote a bunch, should factor out into x minus 2, x plus 5. All right. All right, let's try one more. So nothing different. Still want to justify how many terms we have. I see there's 3. Is there a common multiple? Greatest common factor? We can factor out of each one of them? Well, this is just a 1, so I'm not going to be able to pull a constant out. This guy doesn't have an x, so I definitely won't be able to pull any variables out. But that's okay. We checked at least. In some cases, there will be that option as you proceed with different methods and make bigger polynomials to factor down. So we know that 3-termed expressions, again, have the ability to factor into 2 binomials, right? I know that these first two have to multiply to x squared. And again, since it's just 1, the only multiples of 1 are 1 times 1, and the only multiples of x squared are x times x. So not a lot going on here, again, but we're going down the list of things that must make these two binomials. Again, these two have to multiply to 6. So our options are what? 2 and 3 or 1 and 6. And since these are both 1s, we're looking for the pair that can add or subtract to this middle term, right? Now, if we consider here, 3 and 2 can make 5, right? Because if we were to add 3 and 2 together, we could get 5. But what would the signs need to be? Let's make sure we got that. So since this is a negative, the larger of the two must be negative. So that's the 3. And then what would we do? Would we add 2 to negative 3 or subtract 2 from negative 3 to make negative 5? Well, we would have to subtract them. That way the two negatives being added together makes a larger negative. So negative 2 and negative 3 would make negative 5. That's good. We know that 2 times 3, of course, makes 6. That's why we made it in this list. But a negative number times a negative number is a positive number, not a negative. So even though we got this middle term that we were looking for, we still need to make sure, since we added the signs last, that we get this positive or negative constant out here. Now, the only way we were going to make 2 and 3 be 5, negative 5, is if they were both negative. So we're not going to sit here and start changing these signs, because then it's not going to make 5 again. So since these signs don't make this middle term and this last term, then they don't work. But we do have another option here. Can we make 5 from 6 and 1? Well, we know that the difference between them would be 5. So this would work. But what would the signs need to be? We said that since this is negative, the larger of the two need to be negative. That'll be the 6. Now, will we add 1 to negative 6 to make negative 5, or subtract 1 and negative 6 to make negative 5? Well, if I put a minus here, they would get bigger. I don't want that. So that means that 1 has to be positive, right? Negative 6 plus 1 is negative 5, right? So that works. We, of course, know that 1 times 6 is 6. That's why we put it in this list to begin with. But a positive number times a negative number is a negative number, which is what we want. So here's the group that we want. Again, since these two are both 1s, it's not going to matter where we put these. So I'm just going to put the positive 1 in the first spot, the negative 6 in the second spot. But again, I'm going to try to redistribute because I just want to make sure I do this correct, right? I want to get that 100. So I'm going to distribute this first term. So if I distribute this first term in this group here, x times x is x squared. X times negative 6 is negative 6x, right? Now I'm going to distribute this second term. Positive 1 times positive x is a positive 1x, of course. And a positive 1 times negative 6 is a negative 6. Now, we'll combine like terms. I only have one x squared term, so altogether I have one of them. How many x terms do I have altogether? Well, there are two of them, but negative 6 plus 1x would be negative 5x's. So that's all my x terms put together. And then I only have one constant left, so I'm just going to drop him down. Now, is this exactly what I had? X squared minus 5x minus 6? Sure, that's exactly what we started with. So again, we know, I'll just bring this down here. Since we checked it all out, we know that this thing will factor into x plus 1, x minus 6. And that's a good example here because sometimes there might be multiple ways we can make that middle term, right? But that's why we're checking these signs as we go to make sure that they work out. Now, even if you don't check them as you go, if you redistribute them and you see that you don't get what you started with, then obviously whatever it is that you set up wouldn't have been correct. So this is like two different checkpoints here to make sure that we got this thing factored correctly, and we can see that we do. So that's a good start on trinomials, factoring trinomials. Right? I'll make another video with this first or leading coefficient term being something besides 1, and we'll practice that. All right.